Hi all, I am going to try to go over these slides with you in this format, hoping that it gives us a running start for doing problems in class. So we're going to go over some kinetics basics. This will hopefully be a review, but it might be a little like dusting off some things that you hadn't thought about in a while, so we'll do that. So I probably should get rid of peanut butter because everybody's like, what is peanut butter? And I don't mean for it to be a thing that you remember. It's just that it's like peanut butter and jelly. These two equations, this one here, and then the one we're going to talk to later about CSS is equal to bioavailable dose rate over clearance. Those two equations are the most important equations in pharmacokinetics and can help you to figure out most problems. Not all, but many. So remember, this is a one compartment linear model. And this basically is, here's our concentration that we're at, and then here's another concentration down the line. And so the relationship between these two concentrations can be described by this function here. So e to the negative kt, with t being the difference in time between these 2 points. So e to the negative kt is actually the fraction of drug remaining at time t. So if we're starting with this concentration, if we want to know this concentration, we start with this concentration and multiply it times the fraction remaining at this time t, and it'll give us that concentration. So here's our initial concentration. If we degrade, this is our second concentration, so the t is going to be the difference in time here from time 0, and the slope of this line is going to be k, right? So this is just a rearrangement of our equation to determine k. This is just a rearrangement of this equation, actually. So if e to the negative kt is, if this is the fraction of drug remaining at time t, 1 minus e to the negative kt is the fraction of drug removed, isn't it, during this time? It can also be, this part here could also be the fraction of steady state achieved at time t. So we can use it either way. All right, how do I advance? I advance somehow. I'm not sure how. Do I do that? Do I do that? Sorry, learning. Okay. Now, if we're doing repeated doses, remember this is just giving one dose, an initial dose, and having that decline. Whereas this is if we give repeated dosing. Repeated dosing, we're going to start having our magic carpet rides come into the equation. So we use the multiple dosing factor or function and the accumulation factor. These are really very similar equations. The accumulation factor takes you to steady state. So it takes you from first dose information to steady state. So if you know the Cmax on the first dose, you multiply it times this and it'll take you to the Cmax at steady state. If you want to know the Cmin, you take the Cmin of the first dose and multiply it times this, and it'll give you the Cmin at steady state. If you want to know what the concentration is at 2.67 hours, in other words, you can take any first dose information and then fast forward it to steady state. That's what this does for you. This does the same thing, but in this case, it's to whatever nth dose. So let's say you don't know if you're at steady state yet, but you want to know what's going to happen at the second dose or the third dose. You just put the 2 or the 3 in there for the n. Okay, so you again multiply your Cmax for the first dose and multiply it times a multiple dosing function to take you to the second or third or whatever dose you would like. Notice how similar these equations are. As this n number gets bigger and bigger, this whole thing goes to 0, therefore making it the same thing as the accumulation factor. All right, what if we're talking about a constant infusion? So we talked about single doses here. Here's when we're doing repeated doses. And now finally, what if we're giving a constant infusion? Here's where we talk about our jelly equation. So it's bioavailable dose rate over clearance. Also, if you have to account for a salt form, you can put that in this equation too. Remember, if you have a drug that has a salt form, as soon as the drug hits the blood, it's going to dissociate, and therefore you're going to be measuring only the active component here. That's why you put the salt form in there, but what you're going to actually measure here is not the salt, not the drug with the salt attached, but just the drug. So the clearance is just for the drug, okay? So you guys know this equation well. This is the same equation we use as for a constant infusion. Notice it's the same thing, only we're not worrying about bioavailability. Why? Because if you're giving a constant infusion, the bioavailability is 1. If you're giving a salt form like aminophylline or something, you will have to continue to put the salt form in there. But notice it's really just the same equation, isn't it? So we put our dose rate in here, our clearance in here, and this will give us our concentration at steady state. Why is this concentration at steady state and not average concentration at steady state? Because this is when we're giving repeated doses, right? So we're giving a dose, we're giving a dose, we're giving a dose. So here, it's the average concentration. If we're giving a constant infusion, it's going to be a concentration. It's not an average concentration. So when we give a short infusion, like how we give many antibiotics in the hospital, we're going to be giving maybe a dose over 1/2 hour or over an hour. That's the same thing as giving a constant infusion, but only for an hour or only for a 1/2 hour. So here is our CSS equation from the earlier page, isn't it? Dose rate over clearance. But then what this allows us to do is say, okay, we're going to start to give our drug and eventually it's going to get to steady state here, right? But what if but this is maybe several hours away. What if we're only giving it for 1 hour? So we're giving our infusion for only 1 hour. We're not going to make it all the way to steady state. We can then, so we'll do that again. So we're going to, here's our concentration at steady state. We're going to stop here at 1 hour. So this would be steady state, but we're going to be not going to steady state, right? So it's going to be the concentration at time t here, isn't it? Which, if we stop our infusion there, then it's going to start to decline again. So this is going to be our Cmax, isn't it? So it is going to be t, but it's going to also be our Cmax. This represents the fraction of steady state you achieve at time t, which in this case is the time of infusion. So if we're giving it for 1 hour, we're going to put a 1 in there, right? So this is actually going to give us our Cmax for a short infusion. Oopsie. You should know this equation well. This is when we give repeated doses. When we finally reach steady state, we're going to have this drug in versus drug out equation that's going to allow us to do a lot of things. All right, I think I'm going to stop there. I'll make another video starting here at bioavailability. Thanks. Bye.